thanks for everyone for joining this morning or this afternoon, wherever you're located. One correction in that very generous introduction. I was the CLA for AR5 on the sea level change chapter, so I'm not currently the CLA for AR6. Given the very interesting range of topics that in the seminar series that Craig's organized, being a geologist, I thought I'd bring my perspective of sort of longer term changes in sea level and see if it's sort of interest, and also talk about some longer term perspectives of future sea level that we've been working on over the last few years as well. So not quite over the same period of time or length of time as we look at in the past into the future, but still sort of approaching geological timescales. And so the talk is going to be divided into two parts. First, I'll talk about the last 4.5 million years. And this has been work done with a number of collaborators, but particularly for the sea level part, the collaborators listed down below include Jeremy Shacken, Yair Rosenthal, David Pollard, Peter Kohler, Dan Schrag, and Pat Bartlein. And this is work that we're just finishing and hoping to submit very soon. So this is brand new. It's been ongoing in preparing it for quite a while, but it's unpublished work. And then the second part of the talk, we'll look at sea level commitment beyond 2100. So here we'll look at into the long-term future, up to 10,000 years into the future. So for the first part, I'm going to go through basically the series of steps in very short order of how we ended up deriving our global sea level reconstruction for the last 4.5 million years. And although these steps are, we need to go through these steps in order to understand how we came up with that reconstruction, the information we came up with in these different steps also are of interest and also relate to the sea level reconstruction with regard to climate and ice sheet interactions. And with that new sea level reconstruction, I won't go into any details of sort of interpreting what it all means, but I'll just summarize the new challenges that this new sea level reconstruction presents to the community in terms of understanding ice sheets. So the first thing we'll look at is what we did was we first derived reconstruction of global sea surface temperature and global mean surface temperature. And to do this, we compiled as many relatively high resolution sea surface temperature records that have been published from around the world that span some or all of the 4.5 million year period of interest. And these are the locations of those sea surface temperature or SST sites where these data come from. And they're based on a variety of proxies. These are different types of geochemical or biological indicators of temperature that are then calibrated or to temperature itself. So this shows the distribution of the data, and the symbols are just the different types of proxies we used. And again, we're just going to sort of get quickly into the results. This is the resulting global change in global sea surface temperature over the last 4.5 million years that we came up with. So we took all these records, we stacked them, and then to come up with this sort of long-term average with an uncertainty on it. So the dark blue line shows the higher resolution reconstruction. The sort of the lighter blue shows sort of a running average through that, and then the uncertainty around it. And the two orange dots are independent reconstructions. One, the oldest one is for the Pliocene period that's been a period of interest for a long time in reconstructing temperature at that time. And then the one at the lower right, the orange dot in the lower right, is a recent sea surface reconstruction from Jess Tierney's work. It was published last year. So we see that's good agreement with these two sort of end members, if you will. And what we can see is this long-term cooling and change in variability in the record. Okay, then what we wanted to do is take that record and derive global mean surface temperature from it. And to do so, we needed to account for the change in land temperature, which is greater than the change in sea surface temperature for a given global temperature change. And so we took model data for a range of climates that are shown here that give the land change and sea surface temperature change. And it was from these data that we used to come up with a scaling of sea surface temperature to global mean surface temperature. So without getting the details of that, but that's basically what we did to come up with our global mean surface temperature reconstruction. And so it's going to, of course, look like the sea surface temperature reconstruction. So the change in global mean surface temperature is shown on the bottom here with the change in sea surface temperature above. But you can see the magnitude of change is greater with respect to the global mean surface temperature. And the orange dots, again, are independent estimates of global mean surface temperature at those two times. But in this case, both are based on models. So the oldest one for the Pliocene is the most recent PlioMIP 2 ensemble estimate of global mean surface temperature at that time. And the orange dot, the most at the younger end of the spectrum, which is the last glacial maximum, comes from just Tierney's work. So then now we were going to use that information and ask the question whether we can use it to derive mean ocean temperature, and then from that derive the deltoid teen of seawater, from which we'll derive sea level. So to get into this, I first want to introduce this record, which many of you are familiar with, and some of you may not be. But this is the in blue is the deltoid teen record measured in benthic forearms. These are little microscopic organisms that live on the seafloor, and an example of one is shown on the upper left there, which is a small benthic foraminifer. You can see the scale bar there. And so the oxygen isotopic composition of these benthic forearms, it reflects a combination of the oxygen isotopic composition of the seawater, which changes as a function of ice volume, and the temperature of the water in which the organism is living. And so you don't know independently, just from measuring the O18 of the forearm, how much of what you measure in it is from seawater changes versus from temperature changes. But in general, the way to look at this blue curve is the more negative values, the values at the top, represent warmer climates and lower sea levels. And as the values increase, that's reflecting colder temperatures and some combination of colder temperatures and increase in sea level drop, sea level fall, or ice volume on land. So conventionally, though, this record, even though everyone acknowledges that it reflects a combination of these two variables, conventionally it's largely inferred to reflect sea level. And so in that regard, we can look at a common interpretation of this record with respect to sea level and temperature, but again, with respect to sea level, this is the way it's often used. We look at the oldest part of the record where the blue, the more negative values at that time period, which is referred to as the Pliocene, would indicate relatively high sea levels, higher than present. And then starting at about 3.5 million years or so ago, the values started to become more positive, indicating an intensification of Northern Hemisphere glaciation. And then from about 2.5 to 1.2 million years ago, during what's called the early Pleistocene, we had the sea level variability that was followed by another period of intensification, which is labeled the MPT, which stands for the Mid Pleistocene Transition, that transitioned from the early Pleistocene to the period generally called the 100,000 year world. And the transition from the early Pleistocene to the 100,000 year world is a transition from smaller amplitude, higher frequency sea level variability to higher amplitude, lower frequency sea level variability. And the Mid Pleistocene transition is that transition from those two states of variability. So this is a common way that this Deltoid record is interpreted. And what I'm showing here now are several different independent reconstructions of sea level. Some are from models. Some are from trying to subtract the temperature from the Deltoid of the Benthic record from a variety of ways. And you can see that in these different reconstructions, note that all of them cover the last 4.5 million years, except for panel B, which is just the last 3 million years. But they have differences among them that you can note. But on the other hand, they all share these general characteristics I just described, which is higher sea levels during the Pliocene, and then this sort of, not all of them show the intensification, but then the early Pleistocene, and then followed by the transition during the Middle Pleistocene to the 100,000-year world. So that transition again from the early Pleistocene world is the lower amplitude, i.e. smaller ice sheet size variability at a higher frequency, to larger ice sheet size occurring at a lower frequency of variability. So in some way or another, most of these show these characteristics. And that's the conventional way of thinking about the sea level history through this period of time. So what we want to do here, though, is further address the question of whether we can also extract the temperature component of the Deltoid of the Benthic record. And in this regard, we ask the question, is there a relationship between our global sea surface temperature reconstruction and mean ocean temperature? So we asked that question thinking that, well, maybe if there is such a relationship, then we can use our global sea surface temperature record as a proxy, if you will, of mean ocean temperature, which we can then use as the means to subtract the temperature component from the Benthic record to get to the Deltoid of seawater, which is our sea level. So in looking around, we looked at a number of different modeling experiments that have run to equilibrium for a given climate change, and found that, this is just some examples of them, but it's pretty consistent, that in general, there seems to be a relationship that a change in sea surface temperature corresponds to an equivalent change in mean ocean temperature. That is, it's a one-to-one relationship. And again, these are just some model results that show this relationship. On the vertical axis here, we're looking at mean ocean temperature, and on the horizontal axis, we're looking at sea surface temperature. And in these cases, and in many others that we looked at, it generally averages around a change of 1-to-1. So thinking about that with terms of taking our sea surface temperature record then as a 1-to-1 relationship to mean ocean temperature, we compared our sea surface temperature record which is shown in these different panels in gray, to independent reconstructions of bottom water temperature that had been done from various sites around the world's oceans, which are shown in panels A through F. And in general, you see a good correspondence that is supporting this sort of 1-to-1 relationship of our sea surface temperature to bottom water temperature. And perhaps most convincing of this is shown in panels G and H at the bottom, which are two periods of time. One is from 160,000 years ago to 60,000 years ago, and one is the period of the last deglaciation. And shown in the green dots are the actual data for reconstruction of mean ocean temperature that have come from recently from the ice cores, and specifically Jeff Severinghouse's group, using the gases in the ice cores to derive mean ocean temperature changes. And you can see, again, good agreement between our sea surface temperature reconstruction and their estimates of mean ocean temperature. So we felt pretty confident of this 1-to-1 with some uncertainty around it relationship as a means to derive the mean ocean temperature signal in the deltoid of benthic forearms. However, when we looked at longer periods of time, and now we're looking in these 4 panels at the last 4.5 million years in each case, And in each case, these are different reconstructions. Some are low resolution, some are higher, some are, and the two above are based on one proxy of bottom water temperature. The two below are derived on different means. But in all four cases, what we can see is there's, again, fairly good agreement over the last million years or so between our sea surface temperature and their estimates of bottom water temperature. But from about 1 million years ago to older, to as much as 4.5 million years ago, there seems to be a deviation from the two, whereby the estimates of bottom water temperature are not changing at the same rate as in the sea surface temperature. And so what we did was we played around a bunch of ways with how we could come up with the best relationship of these data to our sea surface temperature reconstruction, and found that with uncertainty, it appears that the relationship of sea surface temperature or mean ocean temperature to sea surface temperature changed from a one-to-one relationship for the last roughly 800,000 years ago. And it gradually changed from what we can infer to a scaling or relationship of about a 0.5 change in mean ocean temperature for a 1 degree change in sea surface temperature. So we use this orange curve, as you see here, as our reconstruction of mean ocean temperature for the last 4.5 million years. So this raises an interesting question itself as to why this change in relationship between sea surface temperature and mean ocean temperature seems to have changed. But we're going to use this relationship now as the basis for deriving or subtracting that mean ocean temperature from the benthic record to get our sea level record. So this is showing now the benthic record on the top, our reconstruction of deep water temperature as represented by delta 18 in the forearm in the middle, and then subtracting that from the benthic record, we end up with our delta 18 of seawater at the bottom shown in blue. So that's what our target was, and that's how we derived it. So the next step is to now take that seawater record and convert it to sea level. So step 3 in our process here, shown in green here, is now how we're going to derive the global mean sea level. Okay, a conventional way to do this is to assume that your delta 18 seawater has a relationship that can be constrained by the change in the delta 18 of seawater at the last glacial maximum, that is about 21,000 years ago, as related to the amount of sea level change that actually occurred at the last glacial maximum. And so several studies have been able to reconstruct the delta 18 of seawater at the last glacial maximum and found that it was about a 1 per mil change. And then reconstructions of sea level lowering at the last glacial maximum generally come in at about 130 meters, giving a relationship then of seawater to sea level change of about 0.008 per mil per meter of sea level change. So that's one conventional way then that people have, many people have reconstructed sea level, is using this relationship. The thing we were concerned about here, though, is that given the extent of time that we're reconstructing sea level over, the temperature, global temperature, clearly is changing over this period of time. And the reason why that's important is because the delta 18 of ice sheets will vary as a function of global temperature change. So the relationship of last glacial maximum to sea level of the last glacial maximum in terms of delta 18 of seawater to sea level may apply for that period of time. But over this period of time that we're looking at, when there's been such a large change in global mean temperature, that's going to imply that the corresponding delta 18 of ice sheets is also going to change. And that must be accounted for. At the same time, we also need to account for, and I'll show briefly why this is the case, the loss of marine-based ice. So that's the ice that's below sea level. And when it's lost, then the basins in which the ice had occupied is filled with seawater. And that also introduces a sort of a quirk into the relationship of deltoid teen to seawater. So without basically, and especially give credit to Dave Pollard here, developed this very elaborate means to come up with the deltoid teen of seawater as a function of global mean surface temperature over our period of interest, the 4.5 million years. But essentially it works like this. This graph is showing sea level on the horizontal axis, the deltoid teen of ice on the vertical axis, and the contour lines you see here is the deltoid teen of seawater. And so what it's showing is, for example, if we take an ice sheet that has an average deltoid teen value of -30 per mil and run across to, let's say, corresponding 70 meters of sea level, then the seawater value would be about 0.6 value per mil. On the other hand, if the deltoid teen of ice were lighter, something like more like Antarctica, so -55 per mil, then for a 70 meter sea level change, we're looking at a deltoid teen of seawater of 1.1. So a fairly large and significant change or difference between the seawater as a consequence or function of the deltoid teen of the ice sheets. So we came up with, and specifically Dave Pollard came up with a means to account for these changes in the deltoid teen of ice sheets as a function of global temperature to derive sea level from the deltoid teen of seawater. At the same time, work by, again, Dave Pollard and Rob DeCanto and Gasson came up with this recognition that the loss of marine-based ice will also influence the deltoid teen of seawater as compared to loss of ice that's not marine-based. And essentially, again, you're filling, when you lose marine-based ice, you fill the basin with seawater, and that corresponding change in the deltoid teen of seawater is not going to be reflected in the same way that land-based ice change would affect the deltoid teen of seawater. So you end up with this sort of jog in the relationship of sea level to deltoid teen of seawater, shown in the lower left corner here by the solid black line, as compared to not a non-marine based ice relationship, which would be shown by the dashed or the gray line. So again, we accounted for these changes in seawater associated with loss of marine-based ice, and these apply mostly to warmer than present climates when we're losing marine-based ice from Antarctica. So to get right to the reconstruction, this is our sea level reconstruction then, after having gone through the various reconstruction or calculations to come up with sea level from the deltoid teen of seawater, accounting for global mean surface temperature and marine-based ice loss. So I'll just show you the reconstruction here, and then we'll see how some of the important points of it, how it compares to others, and then what its implications are. So let's first look at this earliest part of it. This is from 4.5 million years ago to 2.9 million years ago or so. That is, we're looking at the Pliocene, and our reconstruction is shown in the dark blue with the uncertainty. The solid horizontal black lines with the orange uncertainty bars around them are sea level reconstructed from stalagmites in or speleothems in Majorca that was recently published a 1.5 years ago, and that's seeing the age uncertainty on these things, and then the depth uncertainty shown as well by the orange, the height of the orange bars. But these are reasonably well dated given the antiquity of them, indicators, and again, reasonably well constrained in terms of sea level. And you can see our reconstruction falls well within the range of their reconstruction. The black circles are the reconstructions from the work by Ken Miller and others from 2012. And again, showing good agreement with our high stands for that period of time. And then the orange curve is a reconstruction done similarly to what we did, but without getting the details, based on one single record in which they computed the bottom water temperature from a proxy to come up with seawater and then sea level. So, what we can see though is that during this Pliocene period, on average, as has been talked about a lot, sea level was higher than present. And we are in agreement with suggesting that on average higher sea level was about 20 meters or so, with a range of uncertainty. But note the variability that we're capturing as well. So we can see that this period from 4.5 million to 4 million years ago, sea level is remaining above present, but there's quite a bit of variability in that period of time. And then about 4 million years ago, you can start to see fairly large excursions occurring that are increasing and then further increasing and so forth. So I'm not going to get into the details here, but that's just showing what the Pliocene part of it looks like. Now looking at the full reconstruction, the part we just looked at is on the top panel is in the upper left. But now in the younger part, the black circles are in the younger part are again showing independent reconstructions of sea level at those times. And then if we look in the middle, we see these brown and green symbols, and those are showing data, geological data from North America and Europe of times when the extent of the North American and Eurasian ice sheets were at or beyond the extent of the last glacial maximum. So the importance of these data are showing that in this early Pleistocene period, when we have the growth of these large ice sheets at about 2.5 million years ago, that there are geologic data on the continents supporting the existence of ice, extensive ice at those times. Now that just points to the extent of the ice. It doesn't tell us about the volume, but what it's supporting is the fact that we do have evidence of large ice sheets and in terms of their extent, and what our reconstruction is suggesting that they were not only extensive, but also volumetrically large. And I'll show you an example of one of these in a minute. But then on the bottom are two records of ice rafted debris. One in gray is from the North Pacific, and the one in orange is from the North Atlantic. And again, you can see this time when sea level is falling on average with the variability is corresponding to an increase in the ice rafted debris in both of these areas that are would have been receiving icebergs from the North American and Eurasian ice sheets at that time. So looking a little bit more at these terrestrial data, this is kind of interesting. So these early Pleistocene tills, these have been known about actually since the mid-70s. Geologists have known that these tills, these glacial sediments existed that were well beyond the extent of the last glacial maximum. And they were able to date them first by association with, in the stratigraphic record, with the volcanic ashes derived from the Yellowstone caldera eruptions that are well dated. And then more recently by another dating method as well. But on the map on the left, this is the Laurentide ice sheet at the last glacial maximum, and the red rectangle there is outlining the area of the map to the right. And the map to the right now is showing in the darker blue, the last glacial maximum extent, and then the lighter blue, the extent of these older tills or glacial sediments that, again, from a variety of methods are known to be as old as 2.5 million years. And this is that till that it's actually 2.42 million, or 2.42 million plus or minus. And that's this brown horizon you see here. This is in Missouri. This is at 39 degrees south. And it's a till, a glacial sediment deposited by early Pleistocene Laurentide ice sheet as far south as 39 degrees south. That's overlying this more purplish, lighter brown color unit here, which is a soil that was formed before the ice advanced over the site. So it's just a good demonstration of the fact that there is clear evidence that these early Pleistocene ice advances were extensive, and what our reconstruction is suggesting is that they were volumetrically large as well. Now to compare to our reconstruction to those reconstructions I showed you before, you can see the noticeable difference between them, where again, we have on average much more ice than in this early Pleistocene period, especially than in any of these reconstructions. And what we also don't have is a mid Pleistocene transition. So I just want to end this part talking about new challenges that this reconstruction poses to the community. And first of all, the two graphs on the left are showing again our global mean surface temperature reconstruction and our sea level reconstruction. And what you can see is that our reconstruction shows that there were large ice sheets that occurred under a range of global mean surface temperatures. And so the graph on the right is just simply plotting global mean sea level against global mean surface temperature to make that point. And the color coding here on these dots is according to the time. And so the darkest orange on the right are the sort of the Pliocene period when ice sheets did not get as large. But then you can see in the next stage of orange, this is the intensification occurring of Northern Hemisphere glaciation. And then the yellow is the early Pleistocene. And then in the lighter blue is sort of the mid Pleistocene period. And then the darker blue is the last 800, 900,000 years. And so we're getting these very large ice sheets as large as 160 meters sea level lowering. And remember, last glacial maximum was 130 meters lowering under this wide range of global mean surface temperatures. So that's a very interesting result and poses a real challenge as to explaining how that's possible. The next challenge is that we find support for having large ice sheets in the early Pleistocene, again, this period from about 2.5 million to 1.2 million years ago, that is associated with obliquity forcing. So of the three variations of the Earth's rotation about the sun, the obliquity forcing is the change in the Earth's tilt. And we can see the clear, this is at the 41,000 year frequency. And our sea level reconstruction is shown on the bottom. And the middle panel is just showing the change in sea level as a function of time, so the rate of sea level change. But you can see the clear obliquity signal or 41,000 year frequency in our sea level reconstruction. Now, this is not new, but it reinforces the fact that this early Pleistocene was dominated by this frequency of 41,000 year frequency. And you can see that in our cross-spectral analysis shown in the upper right here, which is the dark blue is our sea level and the concentration of variance at about 41,000 years. And then the lighter blue is the variance associated with insolation at 65 degree north in June. So you can see that there's virtually no precession present in our sea level reconstruction. It's all dominated by obliquity. So again, that's not new, but what's new is the fact that these ice sheets in the early Pleistocene were as large as they were. Now, the question of the obliquity forcing in the early Pleistocene itself has been challenging because obliquity forcing is really only restricted to the highest latitudes. And when you move further south, you should expect to see a greater precessional component to the ice sheet variability if they existed at those lower latitudes. And models are able to get obliquity cycles in ice sheets when the ablation zones of the ice sheets are restricted to high latitudes. And that's shown, for example, in this panel on the top here, which is time on the horizontal and latitude of ice extent on the vertical axis. And so this is work by Hybers and Zipperman from 2008, where they forced a simple ice sheet model. And we're able to get these basically 41,000 year variability in ice sheet advance and retreat, as long as the ice sheets remained to the north. But again, what we're finding is that our ice sheets extended down to as much as 39 degrees south, and they were volumetrically large. And Hybers and Zipperman pointed out that with a cooling climate that you would increase ice extent and increase the precessional variability. But again, that's not what we see. We see the increase in ice extent, but we do not see the precessional variability. So that's a perplexing challenge that needs to be addressed as well. And this is just another model simulation by Tabor et al., again with Dave Pollard involved, showing an obliquity forced ice sheet, but again, remaining an ice sheet that's remaining at the higher latitudes and not getting to be as large as the ones we came up. Okay, third challenge is the mid-Pleistocene transition. And again, as I said, beginning, the conventional thinking of the early Pleistocene, of the mid-Pleistocene transition, is it represents a transition from high frequency, low amplitude sea level variability of the early Pleistocene to lower frequency, high amplitude sea level variability. So what we find instead is, well, let's back up a sec. We do see the mid-Pleistocene transition in our temperature reconstruction. So that's shown in the middle and the upper panel here. This is for 2.5 million years ago now, our global mean surface temperature, where we see the early Pleistocene with the lower amplitude, higher frequency transition during the middle Pleistocene to the lower frequency, higher amplitude temperature variability. But that does not, that transition to in amplitude does not occur in sea level. It does occur in frequency. And that's shown by the two cross-spectral plots shown on the left, on the right. On the left, the cross spectra are showing for global mean surface temperature and sea level for the early Pleistocene, with the concentration variance again in the obliquity period at 41,000 years. Whereas on the right, we're looking at the last 800,000 years, where you can see the increase in variance in both sea level and temperature at the roughly 100,000 year frequency. But what we do not see is the increase in the amplitude of sea level. Instead, we have these high amplitude sea level changes occurring throughout. And so that really puts a different flavor on thinking about what the mid-Pleistocene transition is. Okay, let's see. Craig, how am I doing on time here? I see it's almost 8:45. I don't know if I should just stop there and leave questions or delve a little bit into this next part.
I'd like to hear the next part.
Sorry, I didn't realize I was muted. Yeah, I think you should carry on. I think it's
okay. I'll carry on, and I won't carry on too long. All right. So yeah. So this next part is to think about sea level commitment beyond 2100, and the earliest paper work I can find on this, and please let me know if you know of earlier work than this. I'm guessing there probably is. But this is a paper by Philippe Huybrechts and Jan de Vold in 1999 that asked the question about what the response of the Greenland and Antarctic ice sheets would be to multiple century climatic warming. So thinking about response of ice sheets beyond 2100. And in this particular paper, they, given the age of the paper, 1999, they used the IPCC IS-92 scenarios, and then they came up with their own scenarios, but they were quite comparable to the IPCC scenarios of that time in terms of radiative forcing, and that's shown in the lower left up to the year 2100. And then on the right, they show the corresponding mean annual temperature change for those forcings, and then the temperature change is held steady for more or less steady for the period after that up to the year 2500. And so just as an example of when people started to think about sort of these long-term changes in sea level from a change in climate that's occurring over the century. One of the more benchmark papers on this question was this one by Susan Solomon and colleagues in 2009 that looked at irreversible climate change due to carbon dioxide emissions. And at this point, especially through the work of Dave Archer, the idea that CO2 has this long lifetime in the atmosphere, the CO2 we emit has a long lifetime in the atmosphere was now being widely thought about, and the implications of that in terms of irreversible climate change. And so in this regard, what Susan and colleagues did was used a simple carbon cycle model to look at different emissions shown on the left and what the corresponding CO2 concentrations would be for those emission scenarios out to the year 3000. And then in the middle panel with the corresponding surface warming would be, and then finally in terms of sea level, the thermal expansion of the ocean. So here they're looking at, in terms of the sea level commitment, this irreversible change in sea level associated with thermal expansion. This paper by Ricardo Winkelmann and Anders Leverman, Andy Ridgewall, and Ken Caldera was published in 2015 that on the left looked at these different emission scenarios. So a range from 300 roughly gigatons of carbon up to an extreme end of about 10,000 gigatons of carbon, which is approaching using all available and not so easily available fossil fuels. And in this case, then, using a simple carbon cycle model to convert that into atmospheric CO2, and then drive, in this case, they used the PISM model, ice sheet model for Antarctica to come up with sea level change associated with the loss of the glaciation of Antarctic ice sheet for these different emission scenarios. And that's shown in the middle panel, the sea level change associated with just the Antarctic ice sheet. And then what they also showed on the right was looking at the ice loss as a function of cumulative emissions. And so I'm just giving some background here on how this sort of field has been developing and thinking about these long-term changes. So here we're looking at up to 10,000 years now for quite a range of emission scenarios. And now we're also thinking about sea level commitment for given cumulative emissions. So we published this paper in 2016 that basically did a similar thing as what Winkelmann and others had done. But in this case, didn't look at just the Antarctic ice sheet. We looked at the Antarctic ice sheet, the Greenland ice sheet, thermal expansion, and glaciers. So all components of land ice and thermal expansion that go into global sea level. 4 different emission scenarios, and thought about this with regard to multi-millennial climate and sea level change and commitment from that. And then I'm going to compare these results to this paper that just came out last fall by Philippe's group, which is shown here. It came out in our System Dynamics, that also looked at the next 10,000 years of change. Similarly as what we did in terms of looking at all components of the sea level budget. And what this comparison is going to do is illustrate, among other things, some of the challenges that we're facing if we're going to pursue this avenue of research that are going to sound familiar to challenges that we've been addressing for the last 20 years in terms of thinking about changes this century. Okay, so the 4 carbon emission scenarios we used in our 2016 paper are shown here in gray. So these are the emission profiles. So a total emission release of 1280, 2560, 3480, and 5120 gigatons of carbon. And then for comparison, I'm showing the emissions associated with the RCP 4.5 is similar to the lowest emission scenario we considered. And RCP 8.5 has an emission scenario profile comparable to our highest emission scenario. And we'll also compare these again when we compare our results to the recent work by Philippe's group. So these were our results. What we did was we used those emission scenarios, ran them through 4 different carbon cycle models to come up with an ensemble of CO2 change for those different emission scenarios. And that's shown at the top here for the next 10,000 years. And then the global temperature is shown in the middle panel. And then total sea level is shown below. We did, as I said, have results for the individual components of the budget, but I'm just showing the global sea level change associated with that. So, so that would be the sea level commitment for those different scenarios, assuming they were to occur. Now, to compare to this more recent work by Philippe, they looked at different RCPs and a couple of other scenarios. But what I want to show, what I'm showing here on the right, is again in blue our results and in red their results. But just to point out that for the CO2 in red, the higher CO2 concentration you see here of their scenario is actually their RCP 8.5 scenarios, as derived from the very simplified, it's not even a carbon cycle model, it's a parameterized, not even parameterized, it's a simplified way of addressing this sort of decay of CO2 with time. And this is the way that, this is what they derive for CO2 for the RCP 8.5 scenario. Now remember, our highest CO2 concentration is an emission scenario comparable to RCP 8.5. So this points out one problem in comparing results, their results to ours, is that at least with regard to their highest emission scenario, they end up with quite a different CO2 history than what we came up with. The lowest one they have here is their, shown in red for CO2, is their 4.5 RCP, which does agree well with our 1280 gigaton carbon emission scenario, which again is comparable to RCP 8.5. So what their RCP 8.5 CO2 scenario actually ends up looking like, though, is more like our 3840 gigaton carbon scenario. So for that reason, I'm going to compare in the lower two panels their global temperature for that given CO2 profile. Even though it's associated with different emission scenario, this is what the CO2 ends up looking like, which is more like our 3840 gigaton carbon scenario. So compare that scenario, their high-end scenario, to that scenario in terms of temperature. And given that the CO2 is comparable, then we see the temperatures are comparable as well. Even though the models have different climate sensitivities, they're pretty similar, and also for the lowest one. However, what you see on the bottom is this comparison with sea level, and here their sea level estimates are much lower than ours. So this is in part reflecting model dependency, and probably in large part model dependency. I haven't dug into it in detail, but there's just a whole bunch of flags showing up just by comparing these two studies in terms of pointing out that these are apples and oranges and not apples to apples in terms of how you would end up comparing them. So bottom line is they're both clearly showing a sea level commitment, but the response is quite different, both with regard to their way of representing CO2 and in sea level. So that's more of a red flag type of point to make here. Okay, then the last thing I'll just talk about here to finish up is thinking about, this is just a off the cuff thinking that I've been thinking about, is not with regard to these figures, but in terms of sea level, is to think about climate carbon budgets. So in this regard, we have in the upper left, of course, the very well-known relationship between global temperature and cumulative carbon dioxide emissions, and this is from the most recent IPCC Special Report 1.5. So we're all very familiar with this way of thinking about global temperature in terms of as a carbon budget. But other components of the climate system may also relate to cumulative emissions in some way, and that's now been suggested by these two papers that looked in the lower left at the AMOC, the Atlantic Meridional Overturning Circulation, and this is a paper by Bacher et al., where they're looking at AMOC strength on the vertical axis as a function of global temperature change, which through the figure above that, we can associate with cumulative emissions. And so we now think about AMOC change as a function of cumulative emissions. And then the paper on the right is by Knotts and Throve, 2016, where they derive this relationship for sea ice and cumulative carbon emissions. So these are just interesting relationships that not surprisingly exist, given the relationship to temperature, but thinking about in terms of policy, whether as we do with temperature. So we kind of played around with this idea for sea level in this paper shown above here, this sea level commitment as a gauge for policy we published 3 years ago now, which I'll briefly show here. And then I'm not going to get to the last paper here, which is just point out, though, it's very interesting because in this case, Alex Knowles led this study thinking about what the nationally determined contributions from different countries meant about carbon emissions and how that might relate to committed sea level. So if you're kind of interested in this thinking about committed sea level with regard to carbon emissions, this is in this context of the Paris Agreement, this is a really interesting study. But we just took the data we had from our 2016 paper and related it to thinking about global mean sea level change as a function of cumulative carbon emissions. And the two panels here are exactly the same in terms of the axes, but there's a scale change. So the one on the left is showing sea level up to 10 meters and cumulative emissions up to 1,000 gigatons. And then the one on the right is going up to 60 meters and starting at 1,000 gigatons and running up to over 5,500 gigatons. And the idea here is that we can see, let's look at the left panel, that as emissions increase, then of course sea level is increasing for a given interval, and that's what's shown by the different color coding. But if you take a given emissions, then as time elapses and progresses, then the committed sea level from that given emissions increases vertically in that regard. So then what we put on here was the emissions associated with a target of keeping global temperature below 1.5 degrees Celsius and what that would imply about a committed sea level change. And again, this is going up to 9,000 years, so 7,000 years out into the future. And then this would be similar to what Alex did, but before he did it, and he did it a more elaborate way. But to think about nationally determined contributions up to the year 2030 and what that meant about committed sea level, and then nationally determined contributions that would keep global temperature below 2 degrees Celsius and what that meant about. So this is just a thought process because as we've seen, this work on the long-term sea level is going to be very model dependent. And so these results need a lot more studies need to be done to see if this is going to be possible to come up with a reasonable budget for sea level. But it's a thought process about thinking about whether or not we're interested in sea level as a means of keeping carbon emissions below some certain level. Okay, so I just want to end with some questions and challenges from this thinking about commitment. As we've seen, there's few studies existing for the long term to assess model dependency. I think we can be pretty, without having shown the results, we can be pretty confident about thermal expansion. But the ice sheets, as even for this century, remain a real challenge for the future in terms of model dependency and model physics. On these longer term timescales, what we did not consider, but which will clearly become important, are feedbacks in ice sheet response. So as the ice sheets start to deglaciate and the fresh water goes into the ocean, what that does to ocean circulation, how it impacts carbon cycle, the sea level change and how that itself feeds back onto the ice sheet response. And then finally, we did not consider the response of sea level to a lowering of CO2 by carbon dioxide reduction, for example. And I think that's an interesting question to ask is how committed are we if we are able to lower CO2 by CDR? And with that, I will end it and open it up to any questions people have. Thanks very much.
Thank you very much, Peter, for a really fascinating talk. I should get some canned clapter or something. It might be appropriate at this time. Do we have any questions from the group? You could write them in the chat or raise your hand or just say hi. give it a moment. Sometimes people are clamoring. Is there a question?
I have a question, if that's okay.
Yes, please, yeah.
Yeah, thanks, Peter, for a great talk. I have a lot of questions. I'll just limit myself to one, though. Just wondering how might we explain 80 meters of glacial interglacial sea level change in the Pliocene before you have substantial Northern Hemisphere ice sheets? Are you interpreting a kind of revision to the timing of the intensification of Northern Hemisphere glaciation?
So yeah, good to see you, Parker. We sort of think about three phases, if you will, be sort of inception of Northern Hemisphere glaciation, which is when these sort of large ice sheets first appear, but they're sort of infrequent. They're still clearly being paced by obliquity, but not every obliquity cycle results in one. And then we have the intensification from roughly 3 million to 2.5 million, which is a relatively steady increase in the size of the ice sheets on the obliquity frequency, and then into the early Pleistocene. So I would just say that these large ice sheets in the Pliocene, for example, the M2 glaciation, has been known for some time and has represented a challenge for some time. And I would say that our results just reinforce that challenge in terms of understanding how that might have happened. I don't have any bright ideas about it. There was a recent paper that tried to use an ice sheet model and some CO2 reconstruction to see if they could force growth of an ice sheet. I believe it was associated with the M2 glaciation, but didn't get anything near as large as that. So I think it's just one of the many challenges that our reconstruction is. In this case, it's reinforcing an existing challenge. And I just
makes total sense. Thank you.
Yep. We have a question in the chat from Gavin, who unfortunately just had to leave and has asked me to take notes of the response. So he's asking, is there a role for further modeling on pinning down the ocean temperature / sea surface temperature relationship, or the relationship to ice volume, and or the relationship between ice volume and O18?
For the first one, I would say yes. We have some ideas as to why that relationship changed roughly 1 million years ago. That involves ocean circulation changes, and so some ocean modeling to test that idea or to investigate the idea in general would be certainly of interest. But I think on the other hand, I have yet to find, and anybody maybe in the audience can help with this, but I've talked to a lot of people, and we have some people on our paper who've also thought a lot about this, as to why today a one-to-one relationship should even exist, why it exists, not why it should exist, but why it exists, why it's 1-to-1 today, and why it's not 0.5 to 1, for example, or point, whatever to 1. Much less why it changed as it did. So, again, it's very consistent in models to run to equilibrium and end up with that relationship, but I have yet to find any work that's actually addressed the question of why it ends up being that way. I'm not sure anybody's maybe identified it as having existed. And then the second question Gavin had was what again? Can you remind Craig?
Yeah, it's about this question of pinning down the relationship between first temperature and sea surface temperature, and then or ice volume and delta O18.
Oh yeah, yeah, certainly. So the modeling that we did for that is mostly just an algebraic model. It's but a more sophisticated ice sheet ocean modeling that would encompass these processes would also be, yeah, a great thing to do.
I may be misremembering, but is the temperature sea surface temperature relationship associated with paleo records for phytoplankton in the surface?
No, these are based on benthic records, so the bottom water.
Okay. Sorry. So we've got a question from Ken Miller. He says he's got to go, so I hope you're still with us. But M2 is a challenge. Seems to require Northern Hemisphere glaciation. Is more of a statement.
Yep. M2, and I'd say we've identified other, maybe not as large, but large, similarly large ice sheet growth, Northern Hemisphere ice sheet growth periods in the Pliocene as well as the M2.
Yeah. We've got a question from Vivian. What are your views on the causes of long-term cooling and sea level fall over the last million years?
So the long-term cooling has actually been over the last 4 million years. We infer that that's from the long-term cooling is associated with a long-term decrease in CO2. But the CO2 proxies, beyond the ice core are kind of all over the place. So it's very difficult to say for sure, how much of the cooling is associated with CO2, given the large uncertainty in the proxy reconstructions of CO2. But we infer that it's due to a long-term decrease in CO2. And as far as the ice sheets are concerned, again, we have large ice sheets throughout the last 2.5 million years. It's just that the variance changes from dominantly 41,000 year large ice sheets to dominantly quasi 100,000 year large ice sheets. And we attribute that change, again, to a change in the carbon cycle that changes the CO2 variability in the atmosphere. And it introduces this sort of long period, quasi 100,000 year variation in atmospheric CO2 that's modulating the ice sheet response to obliquity.
Do we have any further questions from the group? It'd be nice if anyone would like to speak out.
It's getting late.
I was wondering if you'd like to, in this most recent section, you were talking about the difference between your estimate of the could you speak a bit more on the difference between your RCP 8.5 scenario and the other one that you were looking at, the other study, and what might be causing the difference?
The main difference is as far as I can tell, is we used we used 4 different carbon cycle models that are structurally different, but basically capture the main processes of the carbon cycle, some more comprehensively than others, but to come up with the ensemble. Whereas the way that they derived CO2 from the carbon emissions was basically to assume a logarithmic relationship or logarithmic decay of CO2 with time, with some time constant, rather than use the carbon cycle model. So I believe that whatever that's based on is what gives a very different result of CO2 for an equivalent RCP 8.5 emission scenario. Now, and that's what then leads through to explaining the changes in the global temperature and so forth. But then in terms of why the ice sheet responses are so different, though that just must reflect the ice sheet models that were used. They use Psychopolis for Antarctica. We use PISM, and those kind of issues.
The version of PISM that you were using, was the change in the ice sheets a function of just surface temperature, or did it also incorporate ocean variability?
It only included surface temperature. Yeah.
Okay, that's interesting.
Yeah. So again, that's another thing that would need to be investigated.
We have a question from Ron. Is there any chance you'd like to unmute, Ron? It'd be nice to hear some other.
Hi. Yeah, this
Thank
is mainly maybe you answered this in the talk, but I guess I'm thinking of kind of previous estimates of ice volume variability prior to the Mid Pleistocene transition, and it seems like you guys are getting much more variability. I'm just trying to figure out how do I reconcile that. How do I reconcile essentially the small amplitude variations in previous records and the large amplitudes you get here?
That was, I think, #1 challenge I listed there was how do we get these big ice sheets under these warmer climates? So again, I just repeat that, and that's kind of why I showed that field shot of that glacial sediment in Missouri at 39 degrees south. It's 2.4 million, just to reinforce the point that you can put your hand on evidence that these ice sheets were down at those latitudes in the early Pleistocene. Now, and there are many other examples of that. That's not the only one. So, of course, the terrestrial record is more incomplete because of erosion, but nevertheless, there's a number of sites like that that support these extensive ice sheets. Now, and again, that's been known since the mid-70s. And one idea that tried to reconcile that idea with the smaller amplitude ice sheets was an idea that I developed with Dave Pollard called the regolith hypothesis, where we proposed that these early Pleistocene ice sheets rested on a bed of easily deformable substrate everywhere, including over the Precambrian shield, and which was basically a soil that had developed over the millions of years before Northern Hemisphere glaciation, which ended up with sort of flat pancake-like ice sheets that were spatially extensive and could get to Missouri, but were thin, and so therefore did not have as much sea level change in them. And that with subsequent erosion of the regolith through time and stripping off that deformable substrate down to hard bedrock, that increased the friction at the base of the ice sheet, which caused the ice sheet to thicken up or to thicken and therefore become volumetrically larger and still as extensive, which would explain the change in the volume across the Mid Pleistocene transition, and also possibly the change in the response as well to give change in the variance. So, but there's actually I don't know, I've never seen anyone criticize the regolith hypothesis for this idea, but under those warmer climates of the early Pleistocene that we have, we've done for this project experiments with a GCM and an ice sheet and surface mass to compute the surface mass balance. For an ice sheet with that geometry, under those temperatures, that thing would melt away in no time. It would be so out of balance that it just couldn't exist. And actually the thing that gives these ice sheets hope under those warmer climates to survive and be in mass balance is to thicken them up, not surprisingly, right? So you raise the ice sheet elevation up higher in the atmosphere, it gets cooler. And we actually find that if we insert an ice sheet of the size that we're inferring from our reconstruction for the early Pleistocene, that's larger than LGM, even with those early Pleistocene temperatures, we can get an ice sheet in surface mass balance if it's high enough and thick enough of the size we're thinking about. But the challenge, so that gets us to that point, or I said that at least supports these large ice sheets existing under those type of climates. But the bigger question is, how do you get it to grow to that size in that short amount of time? And that we have ideas for, but they're just sort of speculative ideas at this point.
Okay, thanks.
Thank you very much. Do we have any final questions or statements? As Peter mentioned, we're a bit over time, so we should probably wrap up soonish.
Well, I'd like to thank you, Craig, and those who participated for listening in. I really appreciate it. Thank you.
Thank you very much, Peter. A fascinating talk. Yeah, I look forward to adding it to the online repository. Yeah, and if you could recommend any, if you can think of anyone that you'd like to speak in the series, please let us know. It was really great.
I will.
Great to meet you, and thanks again.
Bye.
Thanks everyone. I hope you have a good rest of the day.